Hey guys, what's going on? So today we are going to be talking about the energy for our complex scalar fields. Let's go ahead and get started. Make sure to hit that like and subscribe button. You can go onto my Patreon page if you want to support the channel, or you can become a member here on YouTube. So without further ado, let's go ahead and get started. So we're talking about the energy for our complex scalar fields now, and make sure my volume's all the way up here. And we want to keep in mind here that our complex scalar fields are different from our scalar fields in that they have complex conjugates. Okay, complex conjugates are what happens when you have the number I in your number, right? So suppose you have this z, this complex number z, and this complex number, it has its conjugate. Its complex conjugate is this guy, and that's equal to a minus I b. And at every point in our space, we have a complex number and its conjugate. Okay. What's going to matter here is there's going to be a particle here. This particle is either going to be associated with this guy here or with this guy here. Now, one of these is going to have some probability of having. It's going to be associated to having a probability, and this guy here, whichever one has a higher probability, there's a particle at that point. Okay, that's sort of the mindset we want to keep in mind here. So the big idea again is just that we have complex conjugates now. That introduces a new type of particle to our field. Okay, so let's go ahead and start getting into the math here. This video and the next video might be a little bit heavier with math because we have complex conjugates, and that just makes things a little bit more complex, no pun intended. So we're going to start from our space-time symmetry. We have that the Hamiltonian for our complex valued field is this guy right here. So this isn't that much different than what we've had before. We're just introducing this complex conjugate now. The complex conjugate is this bar, okay? And now things are going to get a little bit weird, a little bit long and ugly because we have this new notation. We want to keep track of what's what. That when I was first going through quantum field theory, keeping track of what is what was the biggest problem for me. But now that I've gone through this quite a few times, it's not as that big of a deal. So we have our complex conjugate fields, okay? And keep in mind that if this was a real valued field, not a complex value field, then this would just reduce down to a regular Hamiltonian, right? These guys would no longer have bars on them, and we just get the regular Hamiltonian back. Okay. So in some sense, this is a more generalized notion of our scalar field. Okay. And so inside some volume. So some space-time volume, we have a Hamiltonian, right? So this is our Hamiltonian density. Inside the volume gives our total Hamiltonian for the field inside some volume, okay? The picture we want to keep in mind here is suppose we had some volume, okay, where that's given to us by this thing here. And we have our quantum field inside this volume, right? We have our quantum field inside this volume. And we want to know what the Hamiltonian is inside that volume for our field. Our Hamiltonian, we're going to have particles in this volume, and collectively we can construct a Hamiltonian inside that volume. And so that's what we're going to do. So we just plug this in, and then we remember that we've derived all of these things in terms of our A and B constants. These were the coefficients on our solutions for the Klein-Gordon equation. And we calculated all of these already, okay? And so literally we're just going to plug these things into here and see what we get, all right? So, okay, this is going to get really ugly, but let's go ahead and get started. So we're plugging in these two guys, which is here and here. Right? So we have these two guys. So we're going to get these two guys here. These i's are going to go to -1 times two negatives. So that's going to be minus times the minus sign. That's going to be actually no, not 2 times 2i, 2 negative, right? Because we are, this is going to be omega and omega squared, and then I times I is going to be -1 times the other negative is going to give us positive. All right, so this, but we're going to keep this at prime because we're going to do this at k prime. All right, so this is our volume in space, but as we've been doing, I might not have explained this in the past, but this is over one frequency and then over another frequency. But what we're going to do is we want to count everything with having just one frequency. That's where the Fourier coefficients, that's where the Fourier identities are going to take place here. So right now, this is the most general we can get. This we would stop here, right? We'd stop at this point if omega and omega prime were not the same, essentially, right? So this k prime is not the same as this k because it's got a prime on it. So this thing is the most general we can get. We can flesh all this out then, and this is going to get pretty ugly, but again, this is the most general we can get. And in doing that, again, we have omega and omega prime. So if we could stop here, right? We could stop here. We could say, well, we are integrating over this momentum, and we're integrating over this momentum. But the idea is we just want to integrate over one momentum. And so to do that, we recall our identities from Fourier analysis, which are these guys. And so again, this is a wave at a frequency k minus k prime. So we're going to have a spike at k minus k prime with this normalization factor out in front, right? And then k plus k prime, we have this, and the reason we have, again, this -2i omega t is because when this gets all fleshed out, our time components have our omega minus omega prime, our time components down here, omega plus omega prime. But then when we get rid of the prime, this is just going to be omega minus omega, which is going to be 0, and e to the 0 is just going to be 1, and then omega plus omega, well, it's going to be 2 omega, and that's where we get this guy here from. So again, the idea is that we're collapsing all of these down to, or we're going to collapse all these down to a spike. In collapsing down to a spike, that's essentially the same thing as integrating over one momentum, not two momenta. Okay. All right. Applying these is going to give all of these Dirac deltas. Okay. And so you can pause the video if you want. I'm not going to go through all of this, but this is what you get. And then integrating over all the delta functions, we're going to get this here. Okay. So this is wildly reduced now. Now we have omega squared, wherein all these k minus k primes are collapsing we're collapsing from k prime. We're making k primes all k's, essentially. We're collapsing k primes to k's. Okay. All right. So we have. All of this gets reduced down to this. We could see this. So take this guy, for example, k minus k prime. That's going to collapse down this k right here. So we get k here. All right. And then same thing here. Again, we get this guy right here. And a lot of these guys are going to be symmetric. So, which is why we have this minus k here. But then all of this here is then going to get reduced because we can recall now the commutation relationships that we established in the last video, and we can simplify the Hamiltonian to this. Now this is wildly reduced, and the reason for that is because we have a lot of commutation relationships that are going to go to 0, right? So we kept this guy. We kept this guy, right? We have alpha, A dagger, A not dagger, and then B. This guy, we kept this guy, and we kept this guy here. And then everything else, right? So this A with B, actually I'll do that in a different color. This A with B here, this B dagger, A dagger, A dagger, B dagger, right? So these guys here, these guys are going to commute to 0. Those are going to commute to 0. And then I will do another eraser. We can do a different color. Let's do green. This guy here is going to commute to 0 with this guy here. And you can see the pattern, right? There's a lot of things that are going to commute to 0, and what we're going to be left with is this guy right here. And we've established the commutation relationships already. The ones that went to 0 give us this. The ones that give us these will give us this then. Where this thing we're going to ignore because we can't measure an infinite infinite energy, because again the integral of the Kronecker delta at 0 is going to be infinite. So we ignore this bit, and we have this right here. These 2's are going to cancel with the half, and so we get this guy right here. The infinite value, okay, so that's, I just said that, right? So this here then is our Hamiltonian. And I have an Hn here, and so let's make sense of this. Let's make this Hn, because what we're going to find is that this was quantized by n. So we can now build the energy eigenstates of the theory just as we did for our real scalar field. So we're going to start by applying our Hamiltonian to some arbitrary energy state and see what happens here. So we're going to apply a not dagger to here. So we're having our Hamiltonian, which is this guy, applying a not dagger and then to an arbitrary energy state. So here's our Hamiltonian, here's our a not dagger, and here is our energy state, where you flesh everything out then, and we get this, all right? And then from here to here then, this is just, so we have a dagger, a not dagger, a, right? So the idea here, so this guy is going to stay the same, right? This guy's going to stay the same. This guy, this is a dagger minus, if we write this out, a dagger minus a dagger a. We have the a dagger minus that. So these two guys are going to cancel, right? And we get a dagger a right here. So we can see how we got from here to here times our a again, which is just right here. All right, and then what we are going to do now is to from here to here then, well, this is our commutation relationship as we've said up here. So we apply our commutation relationship. This guy here stays the same. And then from here to here, we ignore our, or not ignore, right? We collapse k primes down to k. We've been doing that for quite a bit now. We should be able to kind of understand this again. This is part of the Fourier analysis. We have a spike at one frequency, at one spatial frequency, and that spike, that's how the collapsing is done. Okay, and so what we get is this and this, right? Because we are integrating this guy here. So we have, so here's our AK, here's our omega and our omega. And then we have, then we just have the arbitrary energy state because we're integrating over this, right? And that's going to just be 1, which takes us here. And then from here to here, then we just, this is our Hamiltonian, right? This here we just said was right here. And then from here to here, then we have AK, our Hamiltonian, the eigenstate for our Hamiltonian is just our energy, okay? And so we have this, and then from here to here, then we just factor out E and omega, and we get this. We can do the same exact procedure for B of K, and so in the end we get these two guys. And then we can also do the same thing for our daggers, and so we get these two guys. So in total, what we have is our energy, the energy for our field, okay, when we're integrating over some volume, right? So we integrate over some volume of our field, and our field is inside this volume. And our field is, we have these things in here. We can, if we know what these things are, we integrate them over our field. We multiply by this frequency here. We get the energy of our field inside this volume, right? So I'll actually write that down so this is clear. So this is the energy of our field inside our volume. All right. And A is associated with taking away frequency or taking away energy, and B is associated with taking away energy. A dagger is associated with giving energy, and A dagger is associated with giving energy. But this is all within the context of our Hamiltonian. What we're going to find later is that in the context of something called a number operator, N, for our A field, and N for our B field, where this is for our field, and this is for our complex conjugated field. When we have these things applied to these guys, we're going to be subtracting and adding particles into our volume. Okay, so these things these are creation and annihilation operators, but they only make sense physically within the context of this H or these N's. We're going to take a look at these also later. All right, so to top things off here, we can calculate the momentum of our fields also. So just like we did before when we looked at our Hamiltonian, let's look at the Hamiltonian, this guy right here. We can construct the same thing for our momentum, right? Because our momentum, recall, was, let's see if I actually don't have this on here, but we calculated this from our energy momentum tensor, right? So T mu nu, that was equal to the change in our Lagrangian, d mu of our field, and then times d mu of our field minus Kronecker delta mu nu. Actually, this should be nu, right? This should be nu, and then times our Lagrangian, right? So that this guy, when we do this, we get our Hamiltonian, and when we do this, we get our momentum, right? So we just change these indices, and when we do that for our momentum, we get this thing. Okay, and then inside a volume, we can calculate the momentum of our fields inside some volume, where we just put this into our momentum density. Okay, we're not going to go through this because this is going to be another video. And so once we're done with that, what we'll get is this, right? So I'm just getting to the punchline here, because I like getting to the punchline before we actually go through derivations, so we know where we're headed with our derivations. Because if you don't know where you're headed with your derivations, it makes learning this kind of stuff a little bit hard, I think. Because you don't know where you're going, and there's all these numbers, there's all these values, there's all these indices and so forth. You don't know what you're keeping track of. You don't know what's important. You don't know what's less important. So I'm getting to the punchline here. If you look at this, the only major difference is this guy right here, right? Where we have, when we looked at the energy, we had this thing here. So this obeys the special relativity principles, right? Because we have momentum, we have our spatial momentum, and then here this is our temporal momentum, if you will, right? Because when we looked at our momentum, we had our energy, and then we had our spatial momentum. That was our Fourier energy. Here we have the same thing, right? We have K and then omega. So there's a correspondence there, and we are looking at our spatial momentum now for our field inside some volume. So the field itself has like this collective momentum to it because we have particles in that field, and those particles have mass and so forth. And so in total sum, now we have energies and momentum for our field. So this is what this is going to look like. So for our complex value field, we calculated this guy. Now we're going to calculate this guy. In our real scalar field, we don't have these B's, right? And that makes sense, right? Because the B's corresponded to our field that was not complex conjugated, or that was complex conjugated, excuse me. So this is the for this field. These guys were for this field, and here we just have real, so there's no complex value field. So again, we just had a field that was real. All right. So these are space-time symmetries again, right? Because we were looking at this guy here. This is our space-time symmetry, not an internal symmetry. For an internal symmetry, we're dealing with this guy. Remember, this guy. This was this guy here, and for a field like that. That was for our internal symmetry. I'll rewrite that here, right? So our internal symmetry, we had d mu like that. So this is our internal symmetry. Where this now is a total, not total change in our field. But again, when we look at complex valued fields, we have to also consider this guy as well. Okay, and what we're going to find, I'm going to test my memory here, what we're going to find is that, so we have this, so this here is our total change in our field. What we'll find is that this bit here, that is going to be our canonical momentum for our conjugate field. And this guy here is, as you've guessed it, canonical momentum for our field. So there's crosstalk now. There's going to be crosstalk between our fields in terms of the canonical momentum. All right, and then from there we'll be able to make sense of our number operator, right? So our number operator is going to count the number of particles at a certain momentum inside our volume, right? So we had our volume, and inside our volume we had particles, each of which are vibrating. Again, this all comes down again to our harmonic oscillator model. These things are all vibrating at different frequencies, and the ones that are vibrating at high frequencies, we can count those if all the frequencies are the same. So we can assign, say, green particles with K prime, and we can associate these particles with this color as K double prime. We can associate maybe gray particles with triple prime K. These are all different values of K, and this number operator is going to help us count those particles in that volume. All right, and the smaller the volume we get, it's going to be the number is going to be. Okay. So I won't get too far ahead of myself here, but the idea here is then we're going to talk about internal symmetries, which is going to lead us to a nice physical interpretation of what this number operator is going to be, which is going to be counting particles. Okay, this method we're going to use to count particles. This is then going to throw us into the domain of multi-particle quantum systems. All right, we're not going to go too much into that because we want to get straight to spinors. So we might hold off. We might hold off on this, and we'll skip to spinors. We'll construct the Dirac equation, or Dirac Lagrangian then. My L looks like a J. Lagrangian. And then from there, this is typically how the workflow of this goes. From spinors, then we talk about. Actually, after the Dirac Lagrangian, a full analysis of that, which is probably going to take a bunch of videos. Then we go to the Proca Lagrangian, with vector fields. So we have a lot ahead of us, but I'm not constrained to time here. There are spinor fields. I'm not really constrained to time. This is going to be our workflow. We're probably going to cover this stuff last, multi-particle quantum systems, just because we want to get a lot of the math for our spinors and our gauge fields. Gauge fields in order. So with that being said, make sure to hit that like and subscribe button, and I'll see you guys in the next video.